This video is probably the last video before paper 1 on Tuesday. I'm going to focus on thermodynamics. And about 3 or 4 questions I want to look at, which are the questions that repeat themselves over and over again. So now remember that you've got to know your key definitions. Standard enthalpy of formation, atomization, enthalpy of atomization, lattice enthalpy, enthalpy of electron affinity, ionization. All of these definitions you've got to know. And you've got to know what standard conditions are: 298 K, Kelvin temperature, and standard pressure at 100 kilopascals. But the first one, let's look at this question. This is where you are given nitrogen dioxide is formed when magnesium nitrate is hydrated. So basically thermal decomposition. Use the equation and data in table 1 to calculate the temperature at which this reaction becomes feasible. Whenever we are talking about feasible reactions, number 1, write the equation of delta G equals delta H minus T delta S. For a reaction to be feasible, delta G must be 0, which means that when we rearrange this important equation, delta H becomes T delta S, so T equals delta H over delta S. Now note something essential and very important to note, and that is that delta H is in kilojoules per mole, delta S is in joules per mole. So as a general rule, when you work out delta S, divide the final answer by 1,000. So the way we do this calculation, number 1, work out delta H, and delta H is the sum of the enthalpy of formation of products minus the enthalpy of formation of reactant. Now when you have products, oxygen is 0, nitrogen dioxide is 4 times 34, 2 magnesium oxide is minus 602 times 2. So you do sum of that, take away 2 times minus 790, and then delta H comes to 512 kilojoules per mole. A good way to note is thermal decomposition normally is endothermic. Now, with the delta S, again same rule, delta S is the sum of the entropy of products minus the sum of entropy of reactants. This time note that even elements or atoms in their standard states will have enthalpy change, and then the total sum of entropy of products will be 2 times 27, add 4 times 240, add 204, take away 164 times 2, and that gives you an answer of 891. So delta H equals 512 divided by 891 over 1,000, and then the enthalpy or the temperature at which the reaction becomes feasible is 575 K. Here I want to highlight something for you. In this reaction, delta H is positive and delta S is positive. As a general rule, when enthalpy is positive, endothermic, and entropy is positive, then that reaction will be feasible at high temperature. In the case, if delta H is negative and delta S is positive, then that reaction is always feasible because delta G will be negative all the time. So that's two scenarios. The third scenario, if delta H is positive and delta S is negative, then that reaction is never feasible. Delta G is always positive. And you can work that out by using delta G equals delta H minus T delta S. If delta H is positive, delta S is negative, then a negative and a negative becomes positive, and delta G is always positive. And in the last scenario, where delta H is negative and delta S is negative, then that reaction is feasible at a low temperature. So these are a few things you need to know. The next question is bond enthalpy, bond broken, bonds takeaway. And I'm not going to spend much time on that one because I think that's a skill we've covered in year 12. Okay, next one question which I want to look at is the question on calorimetry. The question on calorimetry will always take the following three equations into consideration. Q equals mc delta T, delta H equals Q over N, and density is mass over volume. Three important equations. At this level, you won't get a simple question of work out Q, you're given mass, you're given specific heat capacity, and you're given change in temperature. There's going to be some form of rearrangement here. So let's look at this question. Main thing, some distilled water is placed in a polystyrene cup. The temperature is recorded. 3 grams of KOH is added to the water. Now this is the important thing. This is your solute here. This is your moles here. This is not the mass. So here I would work out moles of potassium hydroxide, which will be N over MR, which is 56.1. The question says the student calculate the enthalpy of the reaction. So delta H there is minus 51.3. N there is 3 over 56.1. And calculate the volume of water. In other words, number 1, Q equals delta H times N, which will be 51.3 times 3 over 56.1. Ignore the sign here now. The sign here is not important. Then, once we've got Q, we are rearranging for mass. So Q here will be, we will rearrange for mass here. Q here is about 2,745 joules because we've multiplied the answer by 1,000. Then using Q equals mc delta T, M equals Q over C times delta T, which is 2745. Delta T is 30.4 minus 18.1, which is 12.3. And 4.18 is your heat capacity. Times that by 12.3, and you get an answer of mass, which depending on where you round off here. So you should get an answer around 50. But it all depends where you are rounding off here really, I would say. And then what about volume then? And then the mass equals volume, because density of water is 1 gram per cubic centimeters. So volume is mass over density, and hence the mass equals density, and that would be your answer for that. Really nice question you are going to get. The other type of a question that always comes up is the enthalpy of solution type question. And this comes up pretty much every year. I don't teach students a specific formula here to do enthalpy of solution. This is what I teach. You've got your ionic solid. It undergoes dissolving. That there is your enthalpy of solution, potassium aqueous and hydroxide. Enthalpy of solution depends on two things, lattice enthalpy and enthalpy of hydration. So enthalpy of solution is a balance between lattice enthalpy and enthalpy of solution. So right at the bottom here, I'm constructing a Hesse cycle. Potassium, gaseous ion, and hydroxide ion. My arrow goes up because lattice enthalpy of formation is the formation of 1 mole of ionic lattice from its gaseous ions. That's minus 789, as you can see there. And then this arrow going up there is the sum of hydration enthalpies. Potassium is minus 322, hydroxide is minus 528. Look at my cycle, root 1, root 2. So in other words, minus 789 plus enthalpy of solution equals minus 322 and minus 528. Rearrange by taking 789 to the other side and you get an answer of minus 61 kilojoules per mole. And note it's only 2 marks. The thing I would like to highlight here is this. If let's say this was magnesium hydroxide, yeah, the only difference here would be that when you do your enthalpy of hydration here, like magnesium 2 plus gas and 2 hydroxide, you would need to multiply the hydration of hydroxide by 2. And if the data was given as lattice enthalpy of dissociation, then the arrow would go down. Okay? And the last thing here now is Born-Haber cycle. Now with Born-Haber cycle, I want you to look at something. Well, actually, there's a 6 marker which is coming up I want to look at. Now, Born-Haber cycle looks like what's on the board there in front of you. Okay? Now, they very rarely ask you to draw a Born-Haber cycle from scratch. So what do we have in a Born-Haber cycle? If that is my enthalpy change, that's 0 there because your elements are there. So we always start with elements. And the solid we are making is sodium oxide. That means that starts with Na, solid, and oxygen gas. You need 2 Na and half oxygen gas because enthalpy of formation is the enthalpy change when 1 mole of a substance is formed from its constituent elements of 1 mole. Then note, you've got atomization of sodium times 2. Here they've done it the other way. They've done atomization of oxygen, then atomization of sodium times 2. I normally do metal first, then non-metal. Then right at the top is ionization of sodium first times 2. So that means 2 Na plus gas and 2 electrons and O gas. Then the arrow goes down, electron affinity of oxygen, and then the second electron affinity of oxygen is always positive because O minus plus an electron becomes O2 minus gas, adding an electron to a negatively charged species means two negative species repel. So you need to add energy, or you need energy to add the electron. That's endothermic. So the second electron affinity is always endothermic. And then this arrow here is lattice enthalpy of dissociation. And the way I always do this calculation, enthalpy of formation root 1, and then that is root 2. In other words, the standard way of doing this calculation is this. Enthalpy of formation equals atomization of metal plus atomization of non-metal plus ionization of metal plus electron affinity of metal plus lattice enthalpy. That's what I always do. Then you've got to look at, are there two, the answer of 2 somewhere. So you go minus 416 equals atomization of oxygen and 2 times atomization of sodium and 2 times ionization of sodium and first electron affinity of oxygen and second electron affinity of oxygen and X. That X is actually lattice enthalpy of formation. When you rearrange this, you will get an answer of minus 2572 if you do the answer according to the way I've done it. Because I've done it as lattice enthalpy of formation. And because the question says lattice enthalpy of dissociation, your final answer has to be plus 2572. That's really important that you know that. And that's really, really important. Another thing I want to highlight in this question is why the lattice enthalpy for oxide is greater than sodium chloride. So you will be expected to compare lattice enthalpies of 2 different solids. Here, let's do this explanation. An ionic lattice is made up of a metal ion and a non-metal ion. And lattice enthalpy is the attraction between the oppositely charged ions. So we will compare the metal ions and the non-metal ions. Well, sodium ion is the same. So we will say the oxide ion. Please note, we are not talking about oxygen. We are talking about the ion. The oxide ion has greater charge than chloride ion and smaller size than chloride. Can you see the word than? Therefore, you have higher charge density in O2 minus, which means smaller ions attract each other much more strongly. Or better to say this, therefore the force of attraction between sodium ion and oxide ion is much stronger than the force of attraction between Na plus and Cl minus, and that is basically the way to answer this. And again, look here, sodium chloride. So enthalpy of solution of sodium chloride gives you Na plus and Cl minus. Same procedure. Can you see hydration on the right, which is minus 364 and minus 406. This time my arrow is going to go down, plus 771. There's X. So X equals 771 minus 364 minus 406. And that's how you would work this out. And that's basically how you would calculate the enthalpy of solution. So just one more. Let's look at this one, because that's the one I was talking about in terms of where you have a group 2 compound. So here, calcium chloride and 2Cl minus aqueous, and right at the bottom you've got 2Cl minus gaseous, and use that to calculate the molecular enthalpy change when calcium chloride dissolves in water. Let's put X there, arrow up there. Calcium hydration is minus 1650 and 2 times minus 364 because you have 2 chloride ions. And lattice enthalpy formation minus 2237. So minus 2237 plus X, note root 1 root 2 equals minus 1650, add 2 times minus 364, rearrange, and you will get X to be minus 141 kilojoules per mole, and that's really it, isn't it? And again, look here, explain why the enthalpy of hydration of fluoride ions is more negative than chloride ions. F minus is smaller than Cl minus. Yes, 1 mark. OF minus has greater charge density. And then look at the second mark. Hydration is where the negative ion is attracted to the delta plus hydrogen in water. So you will say that the attraction between fluoride ion and the delta plus hydrogen in water is much stronger. So that's the key one. And now let's look at this 6 marker to finish off today's video. An extremely important 6 marker. And this sums up what we mean by perfect ionic model and so on. So you've got lattice enthalpies based on perfect ionic model and Born-Haber cycle. Okay, so let's look at it like this, because the question says compare the 3 values based on perfect ionic, based on Born-Haber cycle, and discuss these values. So number 1, look, the first thing I will say is calcium chloride and potassium chloride are 100% ionic solids. Because, okay, I won't write this, but I'll say it. Because the difference in lattice enthalpy of dissociation value between perfect ionic model and Born-Haber cycle model is very, very little. Like here, you've got a difference of 14. Here, you got difference of 11. Whereas for silver chloride, your difference is over 100, about 135 difference. So I'll say calcium chloride and potassium chloride are 100% ionic, and the reason is because there is very little difference in between the 2 values. Whereas silver chloride has a degree or some covalent character. The reason, because there is a large difference between the perfect ionic model value and the Born-Haber cycle value. So can you see what I've done? I've compared that. Then now let's look at their values. In both of the models, calcium chloride has the highest value and potassium chloride has the lowest. So the strongest ionic bond is calcium chloride, and the reason is because calcium ion has greater charge than potassium ion and silver ion. Because the chloride ion is the same, isn't it? And we can say calcium 2 plus is smaller than potassium and silver ions. Which means that calcium ions, the calcium ion has greater charge density. Okay? Therefore, The ionic bond between calcium ion and chloride ion is much stronger than the ionic bond between silver ion and chloride ion. And then you could also say silver ion is smaller than chloride ion. Silver ion is smaller than potassium ion, and therefore the force of attraction between silver ion and chloride ion is much stronger than between potassium ion and between potassium ion and chloride ion than silver and chloride ions. So you can compare there. Lastly, why does silver chloride have some covalent character? Here you will say is that the small silver ion distorts the large chloride ion, i.e. it polarizes the chloride ion. So it attracts some electron density towards itself. And that is how you would tackle a 6 marker on this. So thank you very much for watching this video, and hopefully I hope you find this